with that said, let's begin this chapter. So, we've got 5 objectives this chapter, 5 objectives. So, first objective, we're going to talk about what are called base units and prefixes. The second objective, scientific notation. The third, conversions of units. The fourth, estimating a value based on known units. And the fifth, using what's called dimensional consistency or dimensional analysis. Those are going to be our 5 main objectives. Let's start first. The phrase base units. Base units. What does this mean? The standard value for one, I put that in quotes, of that physical quantity. What does that actually mean? What does one of a physical quantity mean there? God bless. What do you think, guys? Ladies, gentlemen? What does it mean, one of something? Yeah, more.
It's sort of like a unit rate.
Okay, sort of like a unit rate. I like that. That's usually like dollars per apple or something, but I like the idea. It's getting it down to its base. But what is a base unit then? What is an example of a base unit? How about that? What's an example, Seb, of a base unit? Okay, you're on the right track. I like that, Seb. I like that. Yeah.
It's like the lowest whole number of a unit.
Okay, the lowest whole number. So 1 foot, if you stop there, that's good. And then you convert it to 12 inches, then we're talking about 2 different units. So for example, what do we measure distance in SI units? Meters, very good. And this is not obvious. Not everybody knows this. I don't know if everybody took physical science in like 8th grade. But meters are used to measure distance or displacement. So the meter is the base unit. The meter is the base unit of length. And we are going to really only work in SI units. I'm going to have you do a little conversion with English units also here today, just so you see it and you're used to it. But when it comes to calculations and equations, things are going to always be in SI units. Okay? But I do want you to be familiar with converting like feet to yards and feet to inches or miles to feet with a conversion factor given. So the base unit of length is absolutely meters. What is another base unit that either you know or you suspect you may know? Yeah, Caroline? Grams. Now that's an interesting one, right? Yeah, it's the weirdest one. So we'll get to that a little bit later, but the base unit for mass is actually not a gram, it's a kilogram, which is a very, very interesting exception to the rule. Almost all base units do not have prefixes. So for other units, we're not going to have kilo or milli or centi, but for the unit of mass, we happen to have kilogram as our unit. Okay, and that's the mass unit. Again, length, which could be distance or displacement, is in meters. What's the third base unit that we'll probably use a lot? Tomorrow?
Liter.
Say again?
Liter.
Okay, volume, I like it. So for volume, it is liter. We probably won't use it that much, only because, well, I shouldn't say that. If we get to fluid mechanics later in the year, we would use it. Yep. But we probably won't use it earlier on in the year.
Temperature.
Okay, what are you going to use for temperature then?
Celsius or Kelvin.
Okay, Celsius, really Kelvin is what we would use. So for temperature, I'm going to write kelvins. And it's not degrees Kelvin, by the way, which is ridiculous. It's just nomenclature. Degrees Fahrenheit, degrees Celsius. But Kelvin is represented as kelvins. And Rankine is represented as rankins. Rankine is the absolute unit for Fahrenheit scale. Definitely use these later in the year with fluid mechanics and with thermodynamics and heat transfer. But earlier in the year, there's one other unit I still want to get up here. Very good. Time. Time, which is in seconds. Very good, guys. Well done. Well, ladies and gentlemen, because these are really the main base units. If you look at your text, actually, I think your text states all the real base units that exist. And it's only like 7 base units that make up every other possible unit. Does your text talk about the base units? Yeah. So ready for this? It's on page 10 if you want to jot this down. The base units that make up every other unit of all in physics, like if you know electricity, volts, and amps, and coulombs, all of those units come from these base units. So meter we have, second we have, kilogram we have. The other base units that are useful for E&M are current, which is in amps, temperature, kelvins, amount of substance in chemistry was measured in moles, and And then something called luminosity, which is measured in candelas, which is why it's called a candle, candelas, CD. The ones that you need to worry about in this class are on the board. Don't worry about the extras I just said. In this course, these are the ones you need. And the last two, only later in the year, you're going to use those. It's really the first three that will give us almost every other unit we'll use in mechanics. Okay? Those are the first three that are important. All right, so good. Those are our base units, one of any quantity. Let's quickly, a little bit of history. Sometimes in physics, I do like to emphasize history because it is important. All right, we recognize that over time, physics has changed. And if you start looking into the model of the atom from chemistry and physics, you can clearly see how the model of the atom evolved from a simple atom that we thought was just a particle to that plum pudding model, right? The Rutherford model with the electrons dispersed throughout. Then we went to the J.J. Thomson model. Then he found out that there must be a centralized nucleus with a positive charge. So over time, it changed. So we got to the Bohr model, and then the Bohr model is not even really useful anymore. So this is just some history of units, and this is only for length. So to give you an idea of where things come from. So the first distance in Egyptians of length was a cubit, and that was the distance from the elbow to the tip of the middle finger. Reliable? Is that reliable? I should see everybody going, no, not at all. How about the second one? The length of the royal foot of King Louis XIV? That was a foot. Reliable? Unless when he dies, what do we have to do? Yeah, you have to chop off his foot. Right? That's why it's not reliable. Later on, once he's dead, we can have this unit measure anymore. He's buried in the ground, or he's cremated. So these first two units are not reliable at all. Everybody agree with that? But in those civilizations in that time, it made sense. Because it was a standard across the board. It was a standard. I know, ridiculous, but it was a standard. Now, the third value actually does make sense. Okay? And by the way, SI comes from French. The words SI. Yeah. And the French really are some of the founding culture of modern physics, what we use for regular numbers across the board. So the kilogram, which is a certain size of a meteor or a piece of rock, I think it's plutonium it was for a long time, is held in France in a museum. And it's physically measured there, and it's held in a vacuum chamber. But the kilogram, it turned out, was a bit radioactive, the sample they used. Over time, the mass has been changing. So they had to reestablish the kilogram. I'll put that on news forum this weekend if you want to take a look at it. There's an article on that. Anyway, that's just food for thought. So the French Academy of Science in 1783 said, you know what? Even though this is ridiculous, it is consistent. Why is it consistent? Why do I not worry about this being invalid or unreliable? Why is this third one very reliable as a definition? Why do you think it is, George?
It's unchanging.
It's not changing. Hopefully, not changing. Very good. The distance from the North Pole to the equator better not change. And then we take 1/10 millionth of that. 1/10 millionth. Right? Isn't that crazy? 1/10 millionth. Now, with that said, I just want to give you guys an idea of how history plays a role in different parts of physics. Okay, so there will be times I will step back and do a little bit of history now. So some values. These are not values you need to memorize at all. But certain things you should be familiar with. For example, how tall is like an average person? Give me a number. Give me a number. 5'10". 5'6". And look at that. 7. You answered probably the average male height. You probably answered more for an average female height. And it turns out you're both way too high. The average male height is 5'7", 5'6". And the average female is like 5'1", 5'2". For the whole world, not the U.S. Don't forget though, if you go to like Scandinavia, Russia, people are really tall. If you go to Central America, people are pretty short. So different parts of the world, people have different body types. So the general average though is what we're talking about. So you should have some number sense, right? Some number sense. So when I pick this up, I should be like, it's probably like a quarter pound. And a quarter pound, maybe a half. And I know that because I've lifted a pound weight before, 3 pounds before. So when we talk about number sense, that's what I mean. So certain things here, obviously you're not going to know. For example, the distance from the Earth to the nearest large galaxy, the Andromeda galaxy, you're not going to know that. You don't have to know that. So certain values don't make much of sense. But other things do make sense. This one you should know. Well, not should know, but if you know, sorry, I shouldn't assume people know sports, but if you know about a football field, there's 100 yards in a football field, and yards close to a meter. So they're saying it's close to 100 meters. It's not exact. It's close to 100 meters. it's on that order of magnitude, 10 to the second. And then 2 meters, about the height of a person. Because 1 meter is about 3.2 feet. That's a good conversion to keep in your mind somewhere. A meter is like 3.2 feet. So we're talking about, like, in this case, it'd be a little bit over 6 feet. So this is rounding to the nearest integer here. It's probably close to like 1.6 meters. Okay? And then after that, you got some other ones, like a CD. You guys don't use CDs anymore, but it's the diameter of a CD. And then after that, it just gets kind of ridiculous. I mean, no one's going to know the diameter of the aorta. The aorta is your largest artery, not, what's the one? Vein. Arteries away from the heart, veins toward the heart.
What you say was the meters to feet ratio?
It's about 3.2 feet for every meter. And maybe 2 or 3.12, I forget which one. You can even screw it real good. But it's a little more than 3 is what I'm saying. A little more than 3. And the yard is exactly 3 feet, which is why the meter is a little bit bigger than the yard. Slightly bigger. All right, after that, these are other numbers. We'll go to the next slide. Again, I'm just trying to give you ideas of number sense. You don't need to memorize stuff. You should have some number sense when it comes to realistic things. So here, what things are more realistic? Human, right? Maybe an automobile. Probably not anything beyond that. I don't know the weight of an elephant, what a massive elephant. Maybe you guys know that. A honeybee, probably too small. And then after that, it's kind of just ridiculous. So really, at this chart, the only ones that are kind of like logical to know would be like these 3 maybe. Okay? I only know baseball because it's 150 grams, and it says it on the baseball, 150 grams. And 150 grams is 0.15 kilograms. Now, what is a kilogram? A kilogram is approximately, okay, it is 1,000 grams, I like that. Conversion though, what's my number sense for this? Anyone know it?
2 feet, about 2 pounds.
Yeah, it's about 2.2 pounds. Jot that down. Okay, a kilogram is around 2.2 pounds. The only reason I'm giving you these values is because I want you to have number sense. So how much do you think an average human weighs in pounds? How much does an average human weighs? Give me a number.
150.
150, sounds great. But look at this. 70 times 2 is 140, isn't it? So 70 times 2.2 is right around 150. So when you're using your textbook and you see that a boy has a mass of 30 kilograms, it's not like, oh, that's 30 pounds. That's 30 times 2 with a little bit more, another fifth. So it would be 66 pounds is 30 kilograms. Follow what I'm doing there? Okay. So a number sense to have. Automobile. Automobile, when I was a kid, I was taught that an automobile was like a ton. And the word a ton was used very, very liberally when I was a kid. Oh, there's a ton of food here. There's a ton of this. But what is a ton actually? Anybody know what a ton is? 2,000 pounds. So this says 1,200 kilograms. That would probably be what? 2,400. A fifth of that would be 200, 240. That would be 2,640 pounds. So this would be 2,640 pounds. And I used to think it was around a ton for a car, which is around 2,000 pounds. So you have a number sense of what's going on. Okay, but the conversion that you want to know here is a kilo is around 2.2 pounds. Kilo is very common to use when people talk about kilogram. When I say kilo, I don't mean a kilometer, I mean a kilogram. Just like another phrase that is very, maybe jot these things down, because your book uses it this way also. So if you just see a kilo, it means a mass unit or kilogram. If you see something that says like a micron is a micrometer. And that's going to come up to play a role down here with this prefix in this table. Okay, when we get to that prefix. A micron is a short way of saying a micrometer. Not a millimeter, not a centimeter, not a decimeter or a decameter, but a micrometer is used as a phrase as micron.
Why did the metric system's all like 10, 20, 30?
Yeah.
Like, I use the American system, but why is it like...
Oh, why does it suck?
Yeah.
Because we suck. No.
No.
Because it was started by some British people a long time ago, and then the British said, well, this is dumb, we shouldn't really use this. They stopped using it. But because we were colonists from the British, we continued using it. And then because we've been stubborn for 300 years, we still use it.
Got it.
Things should be completely different. You should never be saying temperature in Fahrenheit. It should be in Celsius, not Fahrenheit. Your mass should be in kilo. It doesn't make sense, the other units. Everything is power of twos, not even everything, I shouldn't say that. Only volume is really power of twos. You have the cup, double the cup, you get the pint, double the pint, you get the quart. 4 quarts is a gallon. Like, what? Why is it double and then multiplied by 4? Why are there 12 inches in a foot? You know what I mean?
Yeah.
So the US system makes no sense. The SI system makes perfect sense because of the power of 10. So to answer your question, I think it's just stubbornness at this point. But over time, we've just adopted it because we were colonists from the British. All right, anyway, so my prefix.
So much.
Say again?
We repeated
Yeah, it is kind of weird. You'd think that you would want to get away from a system
We
that
also
was
remove
plotting.
hues from a lot of our words, like flavor. British people put hue and flavor.
Yeah,
and
color.
Yeah.
Yeah, absolutely. But for math and science, we thought, oh, let's just make it more complicated. All right, out of this table, here's what you need to know. Here's what you need to know. I'm going to circle the ones that are useful in physics, or I'll put an asterisk. Mega, kilo, centi, milli, micro, and nano. Okay? The other ones are there. I don't want you to bog yourself down on the other ones. You're not going to have to memorize these for tomorrow, but I'm telling you this, that throughout the year, we will definitely use these, and they will need to be memorized. But it doesn't need to be done by next week. As you use them more, you'll get accustomed to knowing what the numbers mean. Now, what am I getting at here? Let's discuss. So, first, these are all prefixes. So these alter a number by multiplying by some power of 10. So if I have a millimeter, it's like a meter times this number. If I have a centimeter, it's like a meter times this number. If I have a kilometer, what's a kilometer? How many meters? 1,000. Well, what's 10 to the third? Yeah, it's 1,000. 3 zeros, right? That's how you know the number of zeros. 1,000, 3 zeros, number 3. A kilometer is 1,000 meters. So a kilometer is a meter times that number. A megameter is a meter times that number. Actually, put an asterisk next to giga also, and the reason I'm going to say that is because when it comes to computer science, gigabytes, very good. Even terabytes are used nowadays because we have such large storage capacity. But the nice piece about these, take a look. Notice a trend? There's a trend. Yeah, notice that? We really don't care about the units in between multiples of 3 as an exponent. So these units, okay, deca, we don't use that ever. Hecto, we never use that. So after that, it's like 10 to the third, 10 to the 6th, 10 to the 9th, 10 to the 12th, 10 to the 15th. Notice they're going up by 3, the exponent each time. So if you can remember from a computer that it goes kilobytes, megabytes, gigabytes, terabytes, you can just, as long as you remember kilo is 10 to the third, you can just consecutively add 3 to the exponent and get the other ones. So you really don't need to memorize these 3 as much if you can remember that kilo is 10 to the third, and then the next ones go up by 3, as long as you know your computer data storage. But if you're not big on computers, you don't know megabytes are bigger than kilobytes, probably not a good idea to do that. So again, this is one of the few, when it's a micrometer, it is called a micron. Okay, and the other one I said for kilogram is sometimes called a kilo. Okay, and again, I should put quotes around them because it's not technically the right phrase, but it's used so much that you should probably get used to it. A micrometer, the symbol is called mu. We'll talk about it later in the year when we do friction. A micrometer is micron. A kilogram is really a kilo. Shorthand or short word for it. Questions on prefixes. We're going to use them in a moment. How about scientific notation? Scientific notation is exactly this. You know what? All we want is one value or one numerical value to the left, or one digit, I should say, one digit to the left of the decimal spot. That's what scientific notation is. That's all it is. Okay? Nothing more than that. Just putting one digit to the left of the decimal. So let's take a look at some examples of all the stuff we've been going through. So scientific notation, part A, what would it be? In scientific notation, what would part A look like? What would part A look like, George?
5.4 times 10 to the 5.
Now, if I'm going to write in scientific notation, it would be 5.47. So if I'm going to use tenth, what should it be?
10 to the 4. So,
I'm talking about the decimal.
oh, sorry, 5.5.
Yeah. So if I'm going to use scientific notation and I'm getting rid of a little bit of accuracy, I need to round to the nearest tenth and then round up. Okay? Why is it 10 to the 5? Somebody else. Why is it 10 to the 5th as my power here? Regina?
Because you move the decimal place 5 and towards the left to get a single digit.
Very good. Whoops, and I almost screwed that up. 1, 2, 3, 4, 5. Okay? 5 spots to the left. Now, some people have a problem remembering whether the exponent should say 5 or negative 5. Here's what I think about it, right? This number times something with a positive exponent means it gets, and look at my number, is it bigger? So the answer was right. Does that make sense?
Some teachers teach, oh, if you move the decimal to the left, this is positive. That's fine. And then we're going to move this decimal to the right, which will make the next one negative. But why memorize? I don't like to memorize. If I have to, I will. My memory sucks. When I was in high school, I hated biology because I couldn't memorize things. And you guys know from bio, it's a lot of memorization in bio. Physics I love because I understood it, the theory. I don't memorize this at all. I never memorize left to right because what will happen on one unlucky on one test, what do? You'll switch it accidentally. And then it's just a loss of points for no reason. How about part B? Part B. What would that answer be? Juliet, go ahead.
4.8 times 10 to the negative
10 to the negative.
4.
Thank you. Let's take a look. 1 decimal, 2 decimals, 3 decimals, 4 decimal spots to get it there. I agree. And again, 4.8 times 10 to a negative number gets smaller, and that means the answer up here is smaller. So we validate that our answer is correct. Yes, Jack?
For example, in the A, if it asked it in centimeters, you would have to do 10 to the 6 or 7.
Yeah, so we'll start to convert from centimeters back to meters, and we're going to do that with dimensional analysis. Yep, absolutely. I want to go to the base unit there. Yep. Let's quickly do this because I want you to practice this over the weekend. I know the bell's going to ring momentarily. So I just want to quickly talk about conversions. First, anybody know where these places are?
Hawaii.
And they have 2 different units. Why? You know why?
Because people from Asia might come over and join that.
Absolutely. Hawaii is not like a regular continental U.S. where we're always using feet. So when you go near the border in Canada, or when you go to Hawaii, or certain states that might be close to other countries, there's a tendency to see the units in kilometers and meters, and the speed limit as well. If you get near the Canadian border, you see kilometers per hour.